So lecture number 12. Today topic is rank factorization, projector, the important concept, projector, and real rank of real and complex matrix. So these three concepts are very important, especially this rank factorization technique. What is factorization? We know that if A is a matrix and if I can write A as a P into Q, then it's called factorization of A. Something like 6 equal to 2 into 3. So it is just a factorization. So question, can I factorize a matrix? How can I factorize a matrix in terms of two other matrices? Now, this is always we can always factorize like that. If we take a non-singular matrix, say n is A is n cross m, and we take a non-singular matrix, say B is a non-singular matrix, B inverse exists of m cross n, then we have this. So there is a factor, always there is a factorization. Something like if we factorize want to factorize a real number, factorization means it is a product of two different real numbers. So you can always write x into like that, x equal to y, xy into 1 by y, if some for all y not equal. So this type of factorization is not actually desired. This is always we can factorize like that. So something sometimes factorization means it is a factorization with respect to some x equal to say y into z, such that this y or z is not a multiple of unit multiple of x. Unit means the elements whose inverse exists. If some element in ring, we call some elements unit element mean is inverse exists. If inverse exists, we call it the unit element. Now, if it is unit element is there, so you can always write a inverse. So x equal to x a into x inverse, a inverse. So this factorization is not desirable actually. We actually want to know that some y which is not a unit multiple of y should not be like x into some unit element. In that case, it's obvious. So that's why in real, the factorization is not actually interesting. We can factorize any number through any number. Sometimes we call A is factorized through P or A is factorized through Q. One of the factors P or Q, we call A is factorized through P or A is factorized through Q. So any real number can be factorized through any real number other than this 0. Now, but factorization is interesting if unit elements are very less. For integer z, there is only 2 unit elements, 1 and minus 1. Similarly, for polynomial ring of all polynomials, with say coefficient from some other field or maybe coefficient from other ring from Z. This is again ring. This ring has a interesting because the unit elements are very few elements. There are only the coefficient, but the field elements are the unit element. So here the interesting case is if we can write in such a way that A can be P into Q, such that P is not just a into some identity, some unit element or some. We can always do this. So if this is a factorization, then always this is a factorization. If T some T inverse for some T with proper order, and T is a invertible matrix. So we can always do this. So the interesting part is if A has a rank R, so if rank of A is R, say, and P is n cross R and Q is R cross n, then it is interesting. Then this factorization is very interesting, and this is called rank factorization. This rank, because why this is rank factorization? Because the rank of P and Q both should be R then. It is clear. Because if rank of P is not R, it is less than R, then rank of A cannot be R. Because rank of A is always less than or equal to rank of P, as well as rank of A is less than or equal to rank of Q. So number of independent column in P cannot be number of independent that cannot be more than A. If number of independent row column of A is R, then in P into Q, if A equal to P into Q, number of independent column of A is say R, then number of independent column of P cannot be greater than R. Similar for the rows of Q. So it is clear that if A equal to PQ and rank of A equal to R, then if you have another say factorization, say Mn, and if it is say n cross say T and T cross M, it is clear that T must be less than or equal to R. It is clear. Oh, sorry, T must be greater than or equal to R. Sorry, T cannot be less than or equal to R, because rank of M and rank of N so if rank of A is R, and if T is strictly less than R, then what happens? So okay, we just prove it as a homework that if rank of A is R, and if you factorize A in terms of M and N, such that M is N cross T and N is T cross M, then you just prove that T must be greater than or equal to R. Why it is true? Because that T is greater than or equal to rank of M, right? Rank of M, because T is the number of columns, so that must be greater than or equal to rank of M. Oh, right. This is rank of then Mn, and rank of Mn is R. Right. It is easy. It is. So it is clear. Now the interesting case is equality hold if T equal to R. That is called rank factorization. So in that case, what happened? In that case, okay, the columns of P, now number column is R many columns in P and Q many R many rows in Q. So all the columns of P are independent. That means the forms the basis of the column space. So all the rows, all the columns of the P forms the basis of the column space, and all the rows of Q form the basis of the column row space of Q. And clearly the column space of P is column space of A. Just a matrix multiplication by a matrix with the in the right hand side, that means it's a combination of the columns. That means this equivalently, these are equivalent. This T equal to R, in that case is rank factorization. If T equal to this rank factorization, there's a definition of rank factorization. If T equal to 1, then we call this factorization as a rank factorization. And the next condition is the columns of P is a basis of column space of A. Similarly, rows of PQ is a basis for row space of. And one more equivalent condition is this: since all the columns of P is independent, that is called full column rank. So P is full column rank. P is full column rank, and Q is full row rank. Remember that PQ is nothing but the linear combinations of the rows of Q, collection of linear combinations. If you multiplied a matrix by left side, is actually taking a is a list of linear combination of rows. If you multiply in the right side is a list of linear combination of columns. So proof is intuitively clear now. So because the row space of A is same as row space of A is actually row space of Q in this case. So these are all equivalent condition, and this is called rank factorization. And next, the projector. What is projector? One more thing is this: for rank factorization, if it is a rank factorization, then one more condition is hold, that is null space of Q is same as null space of A. Null space of Q is same as null space of A. Row space of P is same as row space of A. Column space of column space of P is same as column space of A. Row space of Q is same as row space of A, and null space of Q is same as null space of A. These are if PQ is A equal to PQ is the rank factorization. One more result. Now, what is projector? What is projection? In previous lecture, we see what is projection. So projection is a linear transformation basically from a vector space to the same vector space. Something like that. If I say in R2, so this is a vector, and if is a subspace, say the blue one is a subspace, red one is a vector, arbitrary vector. The blue is a subspace, and so there is a perpendicular, or may not be perpendicular, maybe may not be perpendicular. One more another line. So this is another subspace. Actually, they are complement to each other. So this is U, and this is a W. So complement to each other. If they're perpendicular, it's called orthogonal complement. So later we see after introducing the inner product, and this vector decompose in two different parts. Parallel. So this is actually this part here to here is a projection of this red vector along this U on U along W. So along W is important. If W is different, then this projection on U, but along W, because that means there is a this vector, the red vector is sum of this projection plus another vector which is actually parallel to this W, which is actually in the space of W. That W means is in the space of W, the vector in W. So we can write this red vector is the sum of two vector U plus W, where U is in U and W is in W, and U and W are complement to each other. then U is called the projection of that U plus W along the surface W. So that we know that is for linear transformation. So same thing is for is a matrix. So matrix actually, you can, for a matrix we can introduce a corresponding linear transformation, and if similar thing can happen if it's a matrix from Rn to Rm, and we can talk about this linear transformation Ax, and since Ax is a linear transformation multiplied by A, we can talk about this if T is a, we know how to define the projection T as a projection along some on some subspace, along some subspace. Similar thing we can do with this matrix. Now one important part is if you project something, T is a projection, then Tx, and if you take again T, then it is again Tx basically. After taking the projection, if you take again that projection, say U is the projection of U plus W on U along W. Now if you take the projection of U again on U, that is the same as that U. That means once this projection this is in the transformation is called projection, and for matrix is called projector. It's basically T square equal to T. The question is this equivalent? Obviously it is a projection, then T square equal to T. So actually projection, if S square equal to A, then it is a projector. So, and we know this type of matrix S square equal to A, it's called idempotent matrix. The important part is idempotent matrix. So projector actually some sort of equivalent to idempotence. So if A is a projector, what is the meaning of A is a projector? That means A is a matrix. And this matrix, this, if you take this range of this matrix, this subspace, better I write this T. So this subspace of Rn. Now this A is actually a projector on this subspace along a complement of this range. So these are actually equivalent condition. If A is a projector, A is a projector, A square equal to A. These two are equivalent. Idempotent. So again, what is the definition of A is a projector? If I say A is a projector, into S along some other, say U here, into U along W. What is the meaning of that? That means the Ax is actually a projector. Ax is a projection of X. Is a projection. Now this projector is a operator, like the function. The function is called projector, and this projection is actually the vector. This Ax is the projection of X into U along W. And if A is a projector for some U and W, then we will call A is a projector. The two terminology. A is a projector into U along W. If I say A is a projector into along W, that means Ax is a projection of X into U along W. Now, if I say A is a projector, what is the meaning of this? A is a projector means A is a projector into U along W for some U and W. You have to find that U and W. For which U and W, and actually it is clear for what is U. U is just the range. U is the range. So since U is the range of this TA. Actually, what is that? If T means it is a column space. Yes, it is a column space. So it is a column space of A. So for any U and W, if it is for U and some U and W, if it is a projector, then it is called A is a projector. Now this projector on or into U S or U along W is a unique. If we change U and W, this is then it is changed. But this projector or these projections all are unique once we fixed U and W both this subspace. Obviously, U and W should be complement to each other. They are complement subspace. So that means a projector is nothing but a idempotent matrix. A projector and projector is an idempotent matrix. One side is very easy. If it is a projector, then it is idempotent. The other side is slightly tough. So how do you prove that if S square equal to A, then why it is a projector? This is not easy. So you have to actually find some equivalent condition. The first is say A is a projector. This one and 1 implies 2 is easy. Now, if there is one more equivalent condition is a null space of A is same as the column space of identity minus A, and you can easily prove from that 2 implies 3. That is easy. If you assume that A square equal to A, then it is clear. It is just null space of A. What is this? Null space of A is null. That means A multiplied by I minus A. You have to prove this is 0, and this is 0. So that means the column space is subset of the null space. And the reverse is null space. Why this null space are the subset of column space? Easily you can check. So it is trivial to check from 2 to 3. From direct to 2 to 1 is not easy. So you have to go through this way. Then the one more condition is the rank of A plus rank of I minus A is n, and this is clear from rank nullity theorem. Just from rank nullity theorem, this is 3 implies 4 is obvious, and 4 implies 5. 5 is the column space of A is same as the column space of A plus the sum. This is a sum, may not be direct sum. Now this sum is direct. It should be direct. It is a projection that sum is direct sum, and that you can prove from this rank 4. So this is direct, and now we can prove from 5 to 1. If this is direct, this sum is direct, the direct sum, then you can show that A is a projector using this direction, because now the column space of A and this column space of I minus A is a direct. Therefore, column space of A basically the projection onto this column space of A along I minus A. This part, this column space of I minus A. So this to a complement. So you need this to find this, and this. If you want to prove A is a projector, then you have to find in which, along what, and into what, and along what. And that is a into column space of A, along column space of I minus A. So this equivalent condition is very important, and the projector is a very useful concept in matrix and this linear transformation. Now, already you see this projector and this idempotent matrix is closely related. Actually, they are very closely related. So, idempotent matrix is A square equal to A. The projector is idempotent matrix, a projector, and projector is idempotent matrix. The projection, actually, projection is in that actually concept of this transformation and the vector, this all this AX. Just S square equal to idempotent, idempotency of a matrix There's no need of some vector space. It's just a very simple algebraic thing. No need of some column space, row space, this vector space concept and this linear transformation concept, x goes to ax. Just a square equal to is a very simple thing. We can easily define without defining this vector space and this linear transformation, a square equal to idempotency. So this is easy to define and easy to check also, but this conceptually, this application of this a square equal to a through this projection is important. One result is very useful result. If a square equal to a, then rank of this a is just the trace of a. So it is a beautiful result. It's rank of a equal to trace of a. We can easily find trace of a. To find trace of a is the easiest thing. Whatever that, find determinant, whether it is singular or not, finding characteristic equations, eigenvalue, eigenvector. These are slightly calculative, but finding trace of some matrix is the easiest thing. Like finding the order of the matrix. Finding the order of the matrix is the easiest. Then the next easy thing is finding the trace. Some of the it should be a should be by the way, a should be a square matrix. Otherwise, a square equal to a can't happen. A square equal to a unless it's a square matrix, it can't be a square equal to a. A square is not defined actually. For only square matrix, a square is defined. Now, rank of a finding trace is very easy. Some of the all diagonal element. So finding rank is then just easy. So what is the proof? Proof is just through rank factorization. So you have a rank factorization. We always have a rank factorization of a. PQ has a rank. The number of column of P is same as the rank of A, and number of row of Q is same as rank of A. Now, since A is a square equal to A, so PQ is actually PQ. Now this PQ is just, you can write this. So remember that P has n cross R. So this Q is R cross n. Now you can cancel this from the left side. You can cancel this by rank cancellation law, because we know this rank of P is same as rank of PQ. So since rank of P is same as rank of PQ, we can cancel P from the both sides. Similarly, since rank of PQ is same as rank of Q, rank of P and Q both is same as rank of A. That is a rank factorization by definition. You can cancel both sides. So we easily find QP equal to then IR. So very interesting. If A is idempotent matrix and A has a rank factorization PQ, then QP is the identity matrix I of order R. Now we know the trace of this identity matrix is R. So trace of QP is R, but easy thing is the trace of any PQ is same as trace of QR. You can easily check this. You can just find the diagonal matrix, the elements of the PQ, and find the diagonal elements of QP. You can easily check that trace of AB equal to trace of DA. That means trace of PQ is rank of PQ. So this is very interesting. There's some equivalent conditions are there on this idempotent matrix. You can generalize these conditions. If A is some A plus, if A is not say, if A may not be idempotent, but if A is a sum of some matrix and is all are square matrix, and this condition one, that AI square equal to A, condition 2 A square equal to A, sorry, AI square equal to I for all I, and A square equal to A, and then 3 is AI into AJ is a null matrix for all I not equal to J. It's like a orthogonality, something like that. It's dot product. And this rank of this is a sum of the rank. Now you can check that 1 and 2 actually implies, if 1 and 2 both happen, then this implies 3 and 4 also. If 2 and 4 have hold, then 1 or 3 also hold. If 2 or 1 or 3 hold, then 1 2 together implies 3 4, 1 3 together implies 3 2 3 2 4, 2 4 together implies 1 3. And this is slightly, say, complicated, but there is a easier version. There is a corollary. If we assume this all are idempotent, A1, A2, A, K are all idempotent, all idempotent, then what happens? Then the sum is also idempotent. If and only if it is clear, idempotent. If and only if and only if it is clear, if you take the square, then if some product term is there, this is null matrix for all I. And there is a very important theorem, it's called Fischer's Cochrane theorem. This is actually very useful for statistics purpose. This matrix actually orthogonality is there. If it is orthogonal, then some normality assumption, this is actually independent. And once it is independent, the distribution, to find the distribution is easy. If it is not dependent, is not independent, then the finding distribution is tough. So actually these are all important for distribution theory. So this is called Fischer Cochrane theorem. This is if A1 A2 N are all Fischer Cochrane. If A1 A2 are N cross N matrix, such that A1 plus A2 plus AN is identity, is a sum is identity. So which is the idempotent matrix, sum is idempotent matrix. Then the following are equivalent. So following are equivalent. What are the following are equivalent? The following are equivalent. Number 1, all these AIs are idempotent. All these AI are idempotent. Clearly, the other equivalent conditions are AI into AJ are null matrix for all I not equal to J, and this rank are equal. So it is just a slight modified version of this theorem. If you just take A in place of I, so the second condition is just I square equal to I is obvious. So one condition is automatically fulfilled. This rank of this A plus rank of AK is just N, rank of A. So idempotent matrices are very useful, and not only useful, it is actually the analysis of this idempotent matrix and all these results are very interesting and easy. Now there is a special type of matrix, is real complex matrix, when the field is real or complex. So we have some extra thing what we can do. So obviously, what is the extra thing for real and complex? What is the extra? Over the field. This real or real is actually ordered field. We have to say ordering. In general field, may not have ordering. In the complex field has no ordering. You can order this actually, but there is not an ordered field. Complex number cannot be make ordered field. You can order, give a partial order, but real number, set of real numbers, field real numbers is ordered field. There is ordering and some extra compactability property with ordering, something like A greater than B, then A plus C greater than B plus C, greater than or equal to. Similar for less than or equal. Now, what is the extra thing we can do with the real number? What we can't do with the any field, any general field? This is interesting. This is A square plus B square. If it is 0, then we can conclude that A and B both are 0. This we can conclude for real field also only. Any general field we can't conclude that. A square is defined, B square is defined, A square plus B square is defined. So A square plus B square 0, the equation is defined. But from that you can't say A square plus B square, A, B both are 0 like a complex field. A, B may not be 0. One is 1, another is I. So for real, this is a very interesting, and for the complex, the same thing is. So in general, you can generalize this: alpha 1 square plus alpha 2 square dot over alpha n square equal to 0 means all the alpha is at 0. And for complex, it is just complex. Take the complex conjugate: alpha 1 bar, alpha 1 alpha 2 bar. If these are 0, then all the alpha is at 0 for complex. And using this using this extra property, we can prove that there's some advantage of this. Take the field as a real or complex, taking over the general field is this: the rank of one important and very useful result is rank of A is rank of A transpose, which is same as rank of A transpose. Obviously, which is rank of A transpose for any real matrix. For any real matrix, rank of A is same as rank of A transpose. That's a very useful in statistics. Also, is very useful. Several times we frequently use this result. Rank of A is same as rank of A transpose. Not only that, actually row space of A, not only the rank, actually the row space of A is same as the row space of A transpose, A transpose A, and the column space of A is exactly the same as column space of A transpose. Not the rank, the whole space is actually equal, and the null space of A is same as null space of A transpose. The null space are equal. How do you prove that? Basically, we also use this technique in the quadratic form. This is if A transpose X is 0, then actually X is 0 vector for real using this. And for complex matrix, if you take the harmonic conjugate transpose, S star X star A equal to 0, conjugate transpose. So this is the advantage of real or complex matrix over the any other field. And for rank, rank of A is same as rank of A bar for complex matrix. This is a very interesting result. So that's all for this lecture.